Okay, so if you're on Zoom, please unmute yourself and ask questions because I will not be able to see the questions that you post on class, unfortunately. Okay, so now we're going to continue, and I will try to tell you a little bit about some of the kind of basics of the defenses that we that basically are put in place in language models through language model alignment. So, okay, so this, just to remind ourselves, this example, Ahmad used a lot, so tell me how to make a bomb, and we want to generate responses that give no harmful instructions. Okay, so let's also remind ourselves how we actually train models. So model training has three stages, two stages. Basically, the first stage is pre-training, where we train for this next token prediction objective on trillions of tokens, so 15 trillion for lambda 3. And that basically gives us a basic model that has language capability. It has a lot of capabilities of interest, but it's not great. It may not be safe. It might not follow user instructions and so on. So we do post-training. So in the post-training stage, we train on some specialized data that capture capabilities of interest, maybe instruction following, maybe some safety traits. So Ahmad talked a lot about reasoning, so we want to actually be able to instill reasoning capabilities in these models, factuality, and so on. So this is the stage. It's actually shorter turnaround, and it's actually very accessible, even to academia to do this kind of research. So, and then once we have a model, we do inference. So inference, I talked a little bit about decoding algorithms. So we talked about sampling. So you generally sample from this model, but then you may do what's called temperature sampling. You want to make the model a bit more deterministic. There is nowadays we do, maybe you want to do pass at end, generate end responses, pick the best one. You do reasoning and things of that sort. Okay, so in this session, we're going to try to understand this alignment process. So alignment is basically our post-training process. We're going to try to understand it through a very, very simplified lens. So hopefully we all can follow what is exactly going on when we do alignment. And we're going to talk about a framework for doing alignment at inference-time. So Ahmad talked a little bit about inference-time defenses. And so I will also talk about what like the fundamentals of this is and why this is maybe a better kind of way of doing defense, especially against jailbreaks. And we're going to talk about a very, very simple algorithm in this space called best of n. And hopefully I will convince you to use it if you're not already using best of n. And yeah, just we'll conclude with some practical issues. So what is alignment? So again, a generative language model is this probability distribution over responses. So we call this pi-ref, it's a distribution over any response that you can generate, given some query. Tell me how to make it. And then we have a reward model. So the reward model captures whether or not this response is good. Now, Ahmad talked about jailbreaking judges, like whether or not jailbreak happens. So you can take the negate that and say, okay, this is how safe I am. So if the jailbreak doesn't happen, I get a reward of 1. If jailbreak does happen, I get a reward of 6. Now, the goal of alignment is generally to improve my expected reward. So maybe decrease the probability of a jailbreak happening. But I also want to remain close to the reference. So there is a reference model. So this is the model that, let's say, I got from the pre-training. So now I'm fine-tuning this model. I do not want to drift too much from this reference model. And I want to improve my my alignment. Okay, that's basically the goal of language model alignment. We generally pose it as this expectation of regard minus some KL constraint. Now, with this formulation, we can actually solve this problem, and I will come back to that in a minute. It does have a closed form solution. So the solution to alignment is actually the reference model. So this is the model that we got from pre-training, exponentially tilted with regard. So 1 over beta times 3. And this is basically, so if we take e to the regard as another generative distribution, so this is basically going to be pi ref exponentially tilted with some other distribution Q. And these kind of distributions have been actually studied in information theory. There is like good properties of them. They lead to some exponential family of distributions and so on and so forth. But before getting into the details, let us actually see how to derive this closed form solution of the alignment. Right? So I said this formulation has a closed form solution. So in order to get the closed form solutions, basically, so this is the expected regard is linear, and then you have basically your KL regularizer. We can actually try to solve this minimization problem. It turns out that eventually this is just equivalent to some KL divergence plus some constants, and in order to minimize the KL divergence, you will have to actually set the two distributions in the KL divergence to be equal to each other, and that actually leads to the basically the closed form solution being of this form, the reference model exponential. Okay, now let us actually try to examine this in a very simplified manner. So I'm going to actually look at a super simple language model. This simple language model is going to only, our alphabet is 0, 1, and 2. So we can only generate zeros, ones, and twos, and that's it. And we're going to just generate one symbol. So this is the language model. We're generating 0 with a probability of 0.5. 1 with probability of 0.3, 2 with probability 0.2. And then we have a regard, this is exponentiated regard. So the exponentiated regard is 0.22, 0.11, 0.67, which means that 2 is more preferred over 0 over 1. Okay. And then we said we have this family of aligned solutions. What do I mean by a family? So we had this beta, which controls the strength of the KL regularizer. And we can actually switch this beta between 0 and infinity. That gives us a family of distributions. Okay, this basically works. Now we can actually go and solve this problem. I said it has a closed form solution. We can get a closed form solution. We can plot the family of solutions for this very simplified language. So the family of distributions is given by this blue curve, where for beta infinity, we are getting the reference model. So basically, if the KL regularizer has infinite strength, we have to actually stay at the reference model. If there is the KL regularizer has no strength, we're going to try to maximize regard. And by maximizing regard, we're only going to generate 2. We're not going to generate 0 or 1. We're going to put all of the weights of the language model on 2. And that's going to be this degenerate solution at the corner of this probability simplex. And then for any other strength, beta strength of the language model, we're going to get a distribution that's going to be here on this simplex. So maybe I should have asked, like, if you're not familiar with the probability simplex, this is basically the set of all distributions that you can have on the ternary alphabet, right? So this corner of the simplex is basically the with probability 1 is only generating a 0. This one is only generating a 1. This is only generating a 2. Any other distribution over 0, 1, 2 is basically given us by these probabilities. And so expected regard, remember expected regard is linear in pi, and that's determines a linear family of distributions. this KL constraint, KL pi ref as a function of pi is basically determines the convex body, and that the contours of that KL constraint is basically going to be a convex shape. And the intersection of this KL and regard is actually going to be the solution to the alignment problem. This is an exponential family of distribution. It has a lot of nice properties. Okay, now there is another thing that basically people have been saying time and again is that, oh, when I do alignment, my model loses perplexity or like entropy, becomes more deterministic. And so it's very clear why that happens, right? So when you actually align a lot, you're going to err on the side of this high reward outcome that is basically at the center of the simplex. We're not really interested in that. We're mostly interested in alignment really around a very finite KL ball around the reference model. And I will try to talk about like what the size of that ball should be. Okay. Now, where do we obtain this reward? So I said this alignment distribution, how do we get to the reward? Let's say for safety, how do we get a safety reward, right? So there are generally two prevalent ways of doing that. One is that I have a data set of prompts, so tell me a joke, and then responses, so this is like a joke, and then whether or not this joke was safe. So some rater actually looks at the joke and say whether or not this joke was safe. So this is similar to a classifier. Now I can actually train another transformer model that basically can give me a score for safety using this kind of data. Another way to train a reward is through what's called pairwise data. So now, what if I have a prompt, tell me a joke, and then I have two jokes, and then a rater's job, rather than saying whether the joke is safe or not, the rater's job now is to look at these two pairs of jokes and say which one is more safe. And I get basically a label for which one of these things is preferred, and then we use a Bradley-Terry model to train basically again a classifier that gives a score for training. I will come back to what a VT model is. But this reward doesn't have to be trained or even differentiable. It can be anything. It can be response length. It can be coming from any heuristic, because in solving reinforcement learning problems, we don't need to have a differentiable reward. And I will try to discuss that in a bit as well. Now, this side-by-side reward modeling that I said we use a Bradley-Terry model, but this has been, like, we have been doing this kind of side-by-side modeling for a long time. If you have played chess, you have probably, or any kind of competitive gaming, you may have seen the ELO rating. So what's an ELO rating? Basically, the ELO rating is determining the probability of a player winning against another player. And that probability is determined by the difference between the ELO scores, and then that goes through some softmax function. And that's exactly what a Bradley-Terry model is as well. So basically, the Bradley-Terry model determines the probability that some response y2, so this is like one of the jokes, is preferred over response y1, which is another joke, is going to be just the sigmoid function of the difference between the rewards that are associated with these two functions, right? So that's basically the model. I didn't tell you how to train it, but this is the general model. Now, how do we train it? We have data of the form, tell me a joke, and then two jokes, one of them is preferred, and then we're going to take the log likelihood of this Bradley-Terry model, and then we're going to actually train it on our data set, the same way that we train any other type of model. And when I say we are going to train it on the data set, what I mean is that we're going to take some base LLM, so this would be, let's say, your Llama 2 model, and then we're going to just fine-tune it using these laws to give us a kind of a reward model. So the only thing that we need to change is that the last head. So it's just going to give us a kind of a score or a binary out. Okay. And then once we have that, we're going to solve our reinforcement learning problem. So the reinforcement learning problem again is maximizing expected reward minus some KL length. But one thing that I have been avoiding so far is that when we solve this reinforcement learning problem, we also have to solve it on a set of prompts, right? So there is a set of prompts over X, so the X is drawn from a set of prompts rho, for which we're going to solve this problem. And it's extremely important to choose this set of prompts, right? Because they need to actually trigger my model for basically getting like a diverse set of rewards so that then I can actually learn from that. And Ahmad talked a lot about jailbreaking models. So jailbreak prompts are like a great contender for safety fine-tuning, right? So if I'm fine-tuning my model on a set of prompts that are just not triggering the model, even if I have the perfect reward, I'm not going to learn anything from that reward. So that's also like there's a fine balance. Okay, now another method that has been very popular is called DPO. So the direct preference optimization was published in 2 years ago in the RIPS 2023. Basically, the basic idea of DPO is extremely simple. So basically, this is the loss function that the DPO tries to optimize. At first, you may be like, where did this loss function come from? It's basically just combination of two very simple things. The first one is that we know that the alignment actually has a closed form solution. So if you take this closed form solution, get rid of this. So if you take this closed form solution, then from that, we know that the reward is basically, you can write it down as the log likelihood ratio between your aligned model and the base. And then I'm going to just take that and plug it into my Bradley-Terry model. And so remember the Bradley-Terry model, this P was just sigmoid of the difference between rewards. So when I plug this in to my Bradley-Terry model, I get this optimization objective. Now, the interesting thing about this optimization objective is that I don't any longer need to train an explicit reward function. It's basically training on this implicit reward function, which now has my new model and the old model, and then I can actually train this to get a new model without training a reward function. So from that point of view, it's actually very appealing, but it has a lot of pitfalls that people have actually discovered in the last couple of years. And so I will try to talk about some of them if we get time. Right. Now there is many more. There is another variant of basically preference optimization is called IPO, identity preference optimization. What IPO does is that says, you know, I don't really care about the expected reward, but rather what we really care about is winning against the base models. So I'm going to define the objective function to be some function of the probability that y2 wins against y1, where y2 actually is coming from the new model, and y1 is a draw from the base model, subject to the same KL divergence. So rather than, because the reward can be of any scale, may not, the raw value of the reward may not mean physically anything. Now, this is now making the objective more interpretable. And there is many, many more. So there is, I think anything PO has been published right now. So there is probably hundreds, if not thousands of papers published in this space. Yes.
The previous slide.
Here or both?
Yes, so here you said that like, so the prompt should be such that you get like safe responses and unsafe responses, right? So that you can differentiate the rewards.
Yes.
But then like, so if the prompts are always adversarial, then you don't basically teach your model to distinguish between safe and unsafe prompts. And that's because maybe the KL helps.
So, Okay, so I think the KL helps you remain to basically close to the model that you started with, because that model is not just for being safe, it's solving math problems, it can do reasoning, it has a lot of other capabilities that you do not want to. So that's what the KL is doing, right? And I will come back to the role of KL a bit more. But then the prompts is that basically in the end of the day, when you have a language model, you want to use it for any prompt, right? So the user should be able to come up with any prompt, and then you, as a language model, you should be able to respond to any prompt. Now, if the prompt is adversarial, you do not want to respond to that, or maybe you want to respond to that in a way that's still safe. But if the prompt is just asking you to solve a math problem, you should also be able to solve it, right? And so these set of prompts, now I didn't say this, we don't have just one regard, in fact, we have many, many regards. Regard capture and factuality, instruction following, math capabilities and other capabilities, and then you want to combine those regards, right? But for each of these problems, you also want to elicit some like hard prompts, like if the set of math problems that I give to my model are so trivial that it can solve all of them, then I'm not going to learn anything from like a math regard that's even if that math regard is very strong, right? Even if I have the perfect safety judge, like jailbreak judge in the world, I'm not going to be able to learn anything from it if I cannot find ways to find holes in basically my response generation part. Right, so these prompts need to be engineered as well.
So these prompts, but do they have a combination of like easy, mediocre, and difficult prompts, or it's just?
So yeah, so you want kind of a comment, but I think it is actually a very good question and a research problem. It's like, what's a good data diet for feeding to your reinforcement learning algorithm? Okay. Again, if you are on Zoom, please unmute yourself and ask questions because I will not see them.
So right now, as the data, you just create a data set.
Yeah. So yeah, you just create a data set and then you feed it to your favorite Q algorithm. Okay, so what is the role of this kind of care regularizer, right? So I think that's the question that you asked. So this care regularizer, in a sense, if you're familiar with distillation, model distillation, so you may have like a large model, you want to distill it to a small model, what do? You generally, you can either create samples from the large model, use that as a data set for training the small model, but there is what's called soft distillation, where you can actually have like some loss function for supervision through the large model to train the small model, and reverse KL reverse KL is actually a kind of a known good objective for this task. And here we have this reverse KL regularizer. It's basically helping you distill your pre-trained model into the new model, and then picking up some new capabilities along the way. Basically, that's kind of one interpretation of that. And exactly this kind of KL regularized reinforcement learning objective, if you have a very simple log linear model, similar to like the ternary example that we discussed, then it actually enables you to exactly multitask between your pre-training tasks. So whatever you were doing to pre-train the model, maybe you solved like basically that came from solving cross-entropy loss on some data set, and your regard optimization. So maximizing regard with basically multitasking on the two is equivalent to solving this KL regularized product. Okay. Now, I'm going to switch gears a little bit, talk a little bit about inference-time alignment methods. So this test-time compute has shown to be very useful for what we mean by test-time compute. Basically, the first thing you can do is to say, oh, I'm going to just sample from my model and see whether or not that solves the problem, right? So let's say I give a math problem to the model, and then the model generates a response, and then I look at the response, whether or not it solves the problem. I'm going to say, okay, this is the accuracy of my model at solving math problems. This plot is from OpenAI, from the old one. And what they're showing is that if you're actually doing more compute at test time, basically now this compute may be like complicated thing or whatever you were doing, you may generate some reasoning traces, you may generate multiple responses, have some judge to pick one of them or like reason through those responses and try to pick one of them and so on and so forth. And if you're doing that, as the amount of compute that you have increases, then you can actually increase your accuracy. Then there is a bunch of methods for doing this. A very simple one of them remains to be best of n, where you generate n responses, you just pick the best one according to a judge. And there is like a bunch of other. Yes.
I don't want able to replicate this plot because when they say the test time compute, it's not clear what they mean. For example, in S1 paper, what happens is that you kind of limit your language model to generate like less tokens. So if you kind of do that, it's obvious that you get a bad result, right? So
Yeah, this plot is not replicable because they didn't disclose how they got this plot. So it's basically, but it just shows that generally you expect with more compute you should be able to get better performance. Right now, the exact scaling of how this scaling, like what it means, I think remains to be seen. Like S1 paper, I think is definitely replicable, but.
yeah, but that's different because you're kind of limiting your token, so of course you do worse. So it's not really using more compute, you're just forcing your model to stop earlier.
Yeah, but so it's also, so you're also using less compute, right?
Yeah.
Okay. So let's talk about best of n. Again, best of n. So what do we mean by best of n? So you have, let's say you have a reference model P, and then we're going to just generate n responses from P. So we're going to draw n times responses. So let's say this is how to solve a math problem. We're going to solve it n times. And then let's say we have a judge that can tell us which one of these solutions is better. And we're going to just pick that response. Also, it could be like, tell me how to make a bomb. We have n responses to that. And then maybe we have a safety reward that tells us which one of these is more safe. We're going to just pick that one and show that to the user. So implicitly, this process is defining a new distribution we're sampling, which I call pi n, where pi 1 is just P, the reference model, and then pi n is now hopefully going to be more safe. Now this is actually pretty simple, right? So it's very, very simple to implement. I'm going to try to convince you today that this is actually extremely effective. And I will come back to this plot. It's almost Pareto optimal, and I will try to tell you why that's the case and what that means. Okay, with that, I'm going to switch gear to tell you a little bit about the work that we did. And I think it's related to a lot of other works that exist in this space around test time alignment. So this particular work that I will tell you about was led by my colleagues Sid and John. So let's go back to this reinforcement learning problem that we talked about. The other problem that was posed in previous slides, this was basically a bandit problem because we were looking at a prompt and then there was a response that got generated. We ignored the autoregressiveness of the generation altogether. Said, okay, here is a response and here is a reward for this prompt and response. Now I'm going to actually consider the autoregressive generation process of the language model. So I'm going to define a different Markov decision process. I'm going to basically take my state in the Markov decision process to be the prompt, which is tell me how to make a bomb, and whatever has been decoded so far. So sure, I can for example, can be like a prefix. And then the next action is going to be the next token that I'm going to decode from this model, okay? So this is now like, am I going to decode help after sure I can or not? That's going to be the action that the model is going to take. And then we're going to define a reward function. So far, again, we have a reward function that can say, okay, this response that you generated in this context, is it safe or not? And the only thing that I'm going to add is that as long as I'm not generating this end of sequence symbol, I'm just going to keep giving a reward of 0. This is like this, we're not inventing anything new. This is how like the game playing reinforcement learning is also solved. Let's say you're playing chess, you have 0 reward until the game ends, and then you get a very sparse reward at the very end. Like, oh, did I win the game? And then from that, you're going to try to reason about all these intermediate steps of the game that you played and whether or not they were good. We know that basically RL can actually do that. We have seen a lot of great game playing agents. And so we're going to try to see whether you can replicate that and get from just this outcome reward, can you learn how to take intermediate decisions? For that, we're also going to define what's a value function. So what's a value function? The value function is going to determine the probability, basically what's the reward that I'm going to get at the end if I keep decoding from a given state, right? So for example, if the prompt was tell me how to make a bomb and then the prefix is sure I can, right? Then the question is, what's the probability that when I finish decoding, the finished decoded sentence is going to be safe? So I'm going to take an expectation over all the decodings of the model until I reach the end of sequence, and then I'm going to look at the final reward that I'm going to get, and then I'm going to basically take this expectation over all these generations. And we're going to define an advantage, so this is just for mathematical convenience. Now I'm going to perturb my language model. So from P, we're going to go to pi, right? So this is basically our goal was to make it more safe. And I'm going to look at the value of x, y, t, and all z's that are now z's drawn from pi, no longer from p. I'm drawing z from pi, and then I'm comparing that against if z was drawn from p. So this v of x and y t is just equal to expectation over z and p of v of x and y t and z, right? So this is the law of total probability. So I'm changing my p to pi, and I'm hoping that I will get a higher reward. So I'm hoping that this advantage is going to be positive. Okay, I'm going to try to align my model. And then I'm going to also define drift, which is a KL divergence. This is now token-wise KL divergence between the two models over this next token, the action that I'm going to do. Okay, so I want to keep that as small as possible. I want to make this advantage larger. And how
This is the next one.
this is just the next token. So P is basically, this is a distribution over the next one. Okay. Now we can define this objective function again. The objective is going to be advantage minus beta times this KL, right? So very similar to before, but now this is defined for a token-wise NDP rather than this kind of a bandit problem that we had. You can follow the exact same proof, and then you can actually, this is linear, that one is strongly convex, and we can derive the optimal policy. We can derive the optimal policy. The optimal policy is going to be the reference model, now exponentially tilted with the value function. Now this value function, if you're following this literature, you may have heard of process rewards, which is nothing but the value function rebranded. So I think we also, in the research community, we like to rebrand all things as new shiny objects.
The optimal.
This is the optimal value function, right? So now if I did have the optimal value function, then the problem was solved, but I do not have the function, right? So that's a very good question. But if I did have the value function, I could actually sample from this, right? Why? Because basically this value function is giving me this probability that I can just take these two distributions, I can combine the distributions, I can normalize it. Why can I normalize it? Because this is a distribution over the next token. Again, remember the alphabet size is 10,000 for 100,000. And so this is something that we can easily do. We can normalize and then we can actually sample from this distribution. Now we do not have the optimal value function. Now, why couldn't we do the same thing for given the previous theorem that we had for the bandit case? Sorry. So we had a closed form solution, right? We had t e to the 1 over beta r.
Yeah, but here we are starting.
V star we don't have. There actually r we did have. Like why couldn't we sample from that distribution? Yeah. So the previous one, again, I said it's a bandit. Like y is the set of all possible outcomes of the language. Right? You can't even compute the normalizer of that distribution. So even though we had a theorem that said, hey, here is the optimal solution, but we can't sample from. So that's basically because the set of all possible, let's say, responses to Terry row is humongous, right? But here the difference is that we're only talking about one token. And one token, the set of all possible next tokens is like 10,000 for 100,000. So we can easily normalize this and sample from it. But then in contrast, here we need this V star, there we needed just R. R we did have, V star we. Okay, yes.
I have lost the plot, so I think we started with inference time. That is
Right.
not efficient. So how is this connected to that?
So I'm coming back to how we're going to use this at inference. That's a great one, right? And the way I can allude to that a little bit. So this is the base model, right? And then at inference time, if we had V star, then we could actually mix this V star with this prose and language model, and we would be able to sample from it. And that would be a sample from the solution to the model, basically, just given the fixed prose and model.
And earlier we couldn't do that because like just you just explained.
Yeah. But we don't have V star, right? So that's the big $1 million question that's still there. So how do we get V star? So we're going to try and train a model V theta. So we're going to train another parametric model that's going to try to act as our V star. So how are we going to do that? We're going to just take a simple L2 loss between V theta and V star, and then we're going to just try to minimize that. Expectation over a set of prompts and some responses from the language model. We're going to try to basically do a distillation, very simple L2 loss to get V theta. But still, we still don't have V star to be able to actually solve this problem either. We're going to simplify a little bit further. And what we're going to do is we're going to actually take a set of prompts. And then for each of those prompts, we're going to sample from this reference model. So sample some response from the reference model. And then we're going to pretend that the value for each step of the way in the generation, so let's say, tell me how to make a bomb, sure, I can help you with that, blah, 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 and then you end up with basically an instruction for bomb, so you get a very low reward. We're going to associate that low reward with the value of every single intermediate step of the way. So from sure I can help, etc. We're going to associate that R with the V star. We're going to replace it with that V star. Why is it a good idea? Because this is an unbiased estimate for the value, right? Even though it's not the actual value, but it's an unbiased estimate for the value. And basically, if we do that, we can prove under some like simplified assumptions that we're going to recover, basically solve the problem that we set out to solve. This is not our work. This actually was done by Gang and Klein in an actual paper in 2021. So this was done in the context of controlling, so it's called control text generation with future discriminators. And basically, what we're showing here is that their work is actually solving an instance of a KL regularized reinforcement learning problem. So this work was done before these alignments and RLHF was quite hot. Okay. And now that we know what we are actually after is a value function, so we can actually do what we call CDQ. So we can actually go back to the Bellman identity. So the Bellman identity is nothing but just the law of total probability. We're saying that the value of x and y t is equal to expectation over now the next token z is drawn from t of the value of x and y t in the next token. So this is basically as long as we haven't finished the decoding, and if the decoding is finished, we know that the value has to be exactly equal to the result. So we can take this Bellman identity and use it to actually train a value function. So this is and the way we're going to do this is that we're going to take the right-hand side of this equation and set it as a target. And this dot is a stop gradient, so we're going to set this as a constant target, and then we're going to do the L2 loss of training this our value network to try to mimic that. And if this was a tabular setting where we didn't have any function approximation, we could actually look at all the kind of all x, y, t, z, like all of the states of our MDP. This is a contraction. It does actually converge in this process, but for a function approximation, we don't know whether or not it's going to converge. But this was the exact same thing was done in 2013 for solving Atari games, and it actually worked out of the box. We actually took it here. We took the same vanilla method, just one run. It worked the first time we tried. Like very simple, it worked. And yeah. So if you're interested in this kind of math and other things, Sutton and Bartow's paper book is a great reference. I learned a lot by reading that 6-7 years ago. They just won the Turing Award, I think very well deserved. You can find out this and many other great things there. Okay, so the question was, how are we going to use all of this, right? So now we're going to come back to this theorem. Now we train a value function, and we have a frozen reference model. So the only thing is that we're going to take logits from both models, we're going to combine them, and then we are going to get this value tilted model that we're going to just directly sample from. So in this case, let's say our goal is to improve sentiment. So this paper will be like this, like reviewed hated. Let's say these are the 4 tokens that model can generate. Let's say the hated has the highest likelihood, but it gets a low sentiment score. And then when we combine these scores together, we get basically the value tilted distribution is now putting a higher likelihood on liked. And then so it becomes more likely to sample this token instead of the other. Okay. Now, another thing that you can do with this kind of now, if you have these process rewards, something that can give you supervision in the middle of the way, you can combine it with best of n. So what do I mean by that? So in best of n, I said we're going to generate n responses and pick the best one. You don't need to now generate n responses. You can generate just n continuations. And these continuations can now be a block of code. So we're going to take a block of n tokens, and we're going to do these n times. And now we're going to score them, but rather than scoring them with reward, we're going to score them with their value. It's like, well, which one of these continuations is more likely to give me something that's safe? And then I'm just going to pick that and drop the rest and then continue decoding. Okay, so just to give an example, will this paper get accepted? This paper, so then let's say there are these 4 continuations that we sample from the model, will be like why is not getting into, etc. The one that has the best sentiment is the first one. We're going to keep that, drop the rest, continue decoding. Yes.
So you can just look at, like you said that you just need n continuations, you don't need n responses. But then you can look at n responses as continuations of starting from start of total.
Yeah, so best of n is basically the same as this method with m going to infinity, right? But the problem with that is that, let's say if I'm asking for a book to be generated, can you write a book on such snakes? Then I have to generate n books and then start scoring them, seeing which one is better, and then only then I can start serving this to the user, right? So the user has to just wait for a long time. The advantage here is that I'm going to start the first 10 words in the book, and I'm going to commit to that, and then I'm going to basically show that to the user as I'm generating the next 10 words and so on, right? Now, obviously, as I'm saying this, you're asking like, well, how do you know this continuation is going to be good? I know it because it's captured by the value function, but the value function has to be actually very, very good, right? The process reward has to actually is doing a lot of the heading.
This is like online.
This is more on the fly, right? So it's kind of you can serve it to the user with low latency. Okay. How much time do we have? 15? 30. Oh, good. So, okay, how do we evaluate a line? Right, so we talked about training time, inference time methods. We talked about, okay, like you're doing these different PO optimizations. Now I also throw a couple other methods into the mix. Like, how do we evaluate? Right? Generally, the gold standard is human evaluation. So you have humans, they use it, they like it, and so that's basically what we do. But we can't just, as a researcher, I can't just be like, oh, I'm like training a model, let me just get 1,000 humans to start looking at it. Like just a turnaround is very, very slow. A faster way of doing this is that if you have some kind of automated eval, like there is now, Ahmad talked about benchmarks for safety and jailbreaks. So you can have like these benchmarks, you train a model, and then you take it to these benchmarks, get some numbers, and then those numbers kind of draw a picture of how things are going and whether or not like this is a good model. It's worth sending to humans and having humans test it, right? But that is also slow. It's like you only can do that with like your final product. It's like, okay, I trained a model, let me actually do it auto eval before actually launching it, or maybe I have like 5 candidates. But as I'm training these models, like on a daily basis, what can we do? So the thing that's widely used is basically trying to put a point in these 2-dimensional plots for alignment methods. And there is 2 axes. The y-axis is what's called win rate. So what's win rate? The win rate is going to determine how often I'm going to win against my reference model. So I'm aligning this reference model. Let's say I'm taking llama 2, I want to make it more safe. So then I'm going to have a judge for safety. This is R is the judge for safety, or like the jailbreak judge that Ahmad said. And then I'm going to generate a response from this new model. So I'm going to now, I have a candidate pi, I have the reference model T, I'm going to generate a response from pi, generate a response from p, and then I'm going to use the judge to say which one is more safe. Okay, so this judge is an automated judge that we're using. It can be a safety reward. So I'm showing numbers between 0.5 and 0.85. Basically, we want, so if the number is less than 0.5, we are doing something definitely wrong. So we want to improve the win rate above 0.5. P against itself wins 50% of the time. We want to win more. So that's basically the y-axis. And the x-axis is the KL divergence between pi and p. So it basically shows how much of the core capabilities of the P model I have been able to retain into pi while increasing the win rate. Okay, so that's basically the 2D evaluation thing. So ideally, I want to just start shooting up from here and make the win rate go close to 100% with zero KL penalty. But that's not always possible, so I will try to talk about like what is the good expectation to have. But generally, we're going to see like some kind of plot that looks like this, that basically improves win rate, but then pays some KL penalty. And I'm showing you KL between 0 and 8, and I will come back to this. This is very important to keep your KL in single digits. If the KL divergence between the two models goes very high, that means your regard hacking, a lot of the capabilities of the model are going to go away and so on. Okay, now how do we estimate KL divergence? We estimate KL divergence via just aggregating the log likelihood ratios of the model. So if we write down what the kind of definition of KL divergence is, KL divergence between two models is going to be KL divergence, basically some expectation over log likelihood ratios of the two models, pi and p. Now, if I have two models, p and pi, let's say I just trained another model pi, I trained a model p, I have the logic, so I have these likelihood ratios, I can just take them and I can compute this log likelihood ratio. It's an unbiased estimate for KL divergence. So I can just use it and then I can estimate my KL. So that's simple. But we don't have the logics for other like these inference-time methods that I just talked about, or like this block-wise controller or best event. And the question is, how can we actually estimate the KL divergence for these models? And it turns out that there is a magical formula that claims that the KL divergence is just log n minus n minus 1 over n. And the formula doesn't depend on anything, doesn't depend on the prompt, doesn't depend on the distribution of the prompts, doesn't depend on the model or anything. So then the one logical question to ask is this formula actually true? And it turns out that it's not true. So you can actually construct a very simple binary language model where the outcomes are just 0 and 1. We can actually in closed form compute the KL divergence, and then we can compare it with the formula. It turns out that the formula has nothing to do with the KL divergence. So in order to understand this a little bit more, we need to think about like, so let's take a step back. In order to get the KL divergence, we need to actually know what the best event distribution itself is. And can we actually compute the best event distribution? And it turns out that we can. The best event distribution is just going to be given by this quantity f n, where f is the CDF of the distribution. Basically, it just captures all responses whose regards are smaller than a particular response. And the difference between f and f minus is just capturing whether or not you consider the equality or not. And then we can actually take this and compute the mass function of estimate. And this is actually extremely simple. it's, if you think about it, when we're talking about best of n, the CDF of best of n is very, very easy. It's just the maximum or reward over some certain responses from the model. We know how to get the CDF of the maximum. It's just basically the CDF to the power n. And then from there you can go to the TMF. So that's basically what this formula comes from. And then using that and some other techniques, you can show that the KL divergence is actually upper bounded by log n minus n minus 1 over n. So this the formula is actually not true, but it's an upper bound of the KL. Oh. Now for best of n, so this for best of n, you can also think about win rate. So in the end, I said on the y-axis we want to put the win rate of the model that we got against the base model, right? So how do we compute the win rate against the base model? So win rate again is basically how often are you going to get a reward that's high. So it turns out that it's actually very, very simple. Let's say I have a reference model. I'm going to draw n samples from the n plus 1 samples from the reference model, randomly associate one of them to my base model, and then the other n to the best of n model. And the best of n model is only going to choose basically the best of those, right? But since I have n plus 1 draws, n of them are associated with best of n model, 1 is associated with the reference model, my best of n model intuitively gets n to 1 chances of winning against the reference model. So the win rate should be n over n plus 1. And that is actually almost true, not exactly true, and it's an upper bound on the win rate of the best of n model. And then with these, we can actually, without even doing alignment, we can compute win rate versus KL trade-offs for best of n. And the win rate versus KL trade-offs for best of n, which is, so these are some bounds and basically approximations involved, but these approximations are valid for the most part for most of the queries that are a bit more open-ended. And then this is what the picture that we see. You can actually improve your win rate to close to 1 with a KL divergence of 4 to 8. Now, those of you who are doing alignment, you may have seen much higher KLs in the literature, so that's not necessary. It's basically an artifact of doing alignment wrong. I've even seen papers published with KL of 1,000, and I'm pretty sure that's a totally degenerate model. So if your KL is 1,000, I'm pretty sure if you're sampling from that model, it's just generating gibberish. It's also very important to look at the outcomes of the model, right? So if to be able to see what is it that's being generated as we're training the model. Now, of course, this has a lot of disclaimers. This is idealistic. There is no generalization happening, and so on. But I think it remains that KL values in single digits is what the target should be. Okay, now let me show you a basically typical win rate versus KL divergence trade-off here. So here I'm showing this control decoding some of the state-of-the-art methods like IPO, DPO, basically solving the KL regularized RL through PPO and so on. And what we're seeing here is that best of n is actually the best win rate versus KL trade-off over all of these methods. And all of these token-wise methods are actually much more dull trade-offs than the very sharp trade-off that you get from the very simple best of n method. And these also the block-wise extensions of best of n also are giving better trade-offs than these token-wise methods. Yes.
The test time compute is different for these models, right? The
test time compute is different, right? But we are just pretending that what we care about is win rate versus KL trade-off. But then yes, you're right that this best of n is expensive at test time. Now, when we published this, a reviewer called us, they basically said, oh, this is, your claim that SLN is getting better, the best responses is nonsense. And so we had to fight the reviewer for a while to convince them that this is, we're not making a mistake here. Okay, now, some of the good things about doing this alignment at inference time is that it's modular. What do I mean by modular? Let's say I have two different rewards. I can just combine the value functions for those rewards at test time with the base model. So now you have three models, you can get logits from all of them, mix them, and sample from that resulting distribution. And that gives you basically, you can just get like a new align model for two rewards for free. Or you can just take this kind of value function for that you trained on one model and just apply it to another model. And it actually also gives you good performance out of the box. It's a little counterintuitive. It's like if I have a value function for llama model for safety, why should it work on Gemma? But it actually does. And so I think we've seen that kind of generalization happen in the past as well.
Sorry, I have a random question.
Yeah.
I missed the first part. All right. So this is pi is the distribution, the aligned distribution, and p is the original distribution. Yeah. So since you're working on KR, what's the ramification? Is it that like, is it the optimization probably going to focus on the mode of the distribution, higher probability regions, and kind of leave the low probability regions because it's KR?
Yeah. So yeah, I think that so it's the KL of pi key, right? So it's basically it's mode-seeking, right? So some of the things that are in the reference model may be filtered, but what we generate is going to be highly likely under the base model, right? Under the reference model. That's basically the ramification of it, right? That's a very good question. So what that means is that so one of the implications, immediate implications, is that if there is something that my model can't do, like it can't add numbers, I can't teach it using correlation, right? Because fundamentally, the KL regularizer is not going to allow you to learn new skills. We're only able to preserve some of the skills from the base model, as much of it as possible, while we're going to zero out some of the skills, and those, like, for example, generating unsafe responses is one of the skills that may have. We're going to zero those out, and then we're going to basically get a new model that generates some subset of the basically whatever the base model was able to generate. So that's a very excellent question. Yes.
Do you update your reference model?
So here we don't, right? So the reference model is frozen.
So the KL just make sure that you are not going off policy, and because you are doing the on policy R, right?
Yeah.
So if you go distance from the where you are, then your samples would not be your trajectories. I think they won't be valid.
Yeah. So basically, so again, I think KL is just helping you not generate something that's not already likely under the reference model, right? So if the reference model thinks that this response is unlikely, we do not want to be learning those things. We do not want to learn anything new. We just want to filter.
Oh, that's come from the intuition that you can write KL as an entropy term, or?
No, so this is basically KL, like this is KL of pi key, it's mode seeking, right? So if something is very low likelihood under P, but it's high likelihood under pi, then the KL is going to blow up, right? So in order to get like KLs in the single digits, we're not going to invent any new knowledge. We're just going to stick to whatever the model already knew. We're just going to filter some of it, right? If you filter something that was likely under P, now make it unlikely under pi, you don't get a lot of penalty for that. That KL pi P is not going to penalize that. Yes.
Is the temperature for each model, is that part of the objective function or is that frozen?
So we use temperature one in training, but that's a very good question, right? So because sometimes when you sample from the models, like there is a cheat sheet from OpenAI where like if you're doing coding, you may want to use temperature 0.2 to 0.4. If you're doing more creative applications, you may want a higher temperature, etc. Right? So that seems to be needed to be part of the kind of training objective. But generally we train with temperature 1. Basically so because the estimating also KL and other kind of quantities when you have a different temperature, that becomes a nightmare of its own. I will, if time permits, I will come back to that question a bit more. Like it's not just temperature, like the actual way we decode from the model should have ramifications on how we do the alignment. Let's say if you're doing reasoning, or like if we know that we're going to use best event to decode from the model. So maybe we should be aligning to have a better performance for that. Or like if we know that we're going to use temperature 0.2 for coding, maybe we should align in a way that my model works best with temperature 0.2. But we don't do that. Like that's not the accepted practice in alarm. So there is that like mismatch between the objectives. And so one other thing is that the inference alignment also helps against adversarial attacks more, right? And part of the reason is that when we do alignment, you're training on a set of prompts, and then we're kind of distilling this kind of more safe model into a new model. And now the adversary can come up and say, hey, you know, you have this model, you aligned it, okay, great. I'm now going to choose my prompt to trigger your model, right? But if you're doing this at inference time, the adversary has to go first. The adversary is going to choose their prompts. And then we're going to actually be kind of defending against the adversary's prompt. And generally, these kind of inference time methods, especially for jailbreaking, are much more safe compared to basically the training solution. Okay, so how much time do we have? 12:15. Okay, great. Okay, so let's go back to this basically the basics that we had here. So we had basically this expected reward minus KL, right? So we said, oh, this is linear in pi, this is the convex, strongly convex in pi. So we can actually solve it, and we can solve it for different depths, right? So that was basically the set of aligned solutions that we got. But given that this is strongly convex, this is linear, it also means that for every given KL, right? If I want to look at a constraint problem, for every given KL level, the value that I get for expected reward has to be maximized by my KL regularized RL solution, right? So it has to dominate, in other words, on the KL versus reward plane, reward versus KL plane. It has to dominate every other method. And specifically, it has to dominate best event. Well, best event has nothing to do with this KL regularized, right? But then we saw here that best event comes on top, everything else is actually predetermined. Even though these, in principle, if we solve these optimally, they should have been on top of best event. So then the question is, what's happening here? It's like, why is best event coming on top? Why these methods that in principle their objective function should dominate best event's objective function, they don't, right? So here I'm just taking one of these very simple language models with like 1,000 outcomes or like 3 outcomes that we talked about, and we're comparing the expected reward we get from best event to what you would get from optimally solving KL. So if we solve KL regularized RL optimally, it turns out that it actually does dominate best event. So that's the good news. So the theory is not wrong. But it dominates it by just a tiny bit. That it's not even visible in this plot. Okay? And best event is almost optimal. And so the reason we see this striking difference in practice is that we don't solve this K-regularized RL optimally, and then we end up with this very dull trade-off, and then the trade-offs we get from best event dominate what we get from the K-regularized. So then the question is, why is that the case? And I'm going to I'm not going to talk about that, but then there is theory that suggests that why best event is almost optimal, and in like what cases, what sense, and so on and so forth. But that also leads to another question. It's like, okay, if best event is that good, can we actually forego our K-regularized RL objective and say, hey, can we actually use best event to train a new model, right? So now that is another way of alignment, is distilling best event. Now, with distilling best event, the first thing we can do is to say, oh, okay, I'm going to take my reference model, and then I'm going to prompt it by tell me how to make a bomb, and then I'm going to get like 1,000 responses, and I'm going to look at which one is the best. I'm going to take that response. Now I have a prompt response pair. I'm going to use that to supervise fine-tune my model, right? I'm going to get a bunch of these. And I'm going to use that as some SFT data set to fine-tune my model. And that's basically what hard distillation is, right? So if you're familiar with distillation, basically in the distillation, you can also take like basically some data set generated by your teacher and then use it to train your student. But then we also know that hard distillation is not great, and you can do a lot better if you're doing soft distillation, right? So if you're basically using your teacher to generate logics or like probabilities, that then you can use those logics or probabilities as supervision signal for your student, you get a lot better distillation, right? And you can actually do that too. And so I told you what the TMF of best event is. You can basically build some math around that and actually use it to do distillation of best event into a new model. Now, when I created these slides, these papers weren't accepted yet. So these slides I actually created in July 2024. But now this one is published in NeurIPS. These two are appearing in this year's like ICLR. So basically, you can actually also use that and distill best event into a new model, and that gives you better performance generally against like this is DPO and TPO, so you get like performance improvements against them. But still, there is some gap between the inference-time best event and what you can distill into a new model. Okay. We have 15 minutes. I'm going to skip this part. So inference-aware model alignment is basically saying if you're using reasoning best event, some other method in test time, or like temperature point 2 instead of temperature point 7, we should actually be using that information to do alignment better. But we don't have time to discuss that. And rather, I will try to talk to you a little bit about the practical issues of alignment and maybe end a little early so that we can have a little bit of discussion. So we talked about a lot, like different methods for alignment and so on and so forth, but then Ahmad also told you a lot about jailbreaking. And every time we come up with a new model, we have like these fancy methods that we try to put into play and launch it, and then researchers like Ahmad come back and come up with new jailbreaks and jailbreak these systems and so on. So why is safety alignment actually hard? Like, why is this a hard problem, right? So we talked about this general objective of maximizing expected reward subject to some KL constraint. And there is some bits and pieces that make this problem hard. Number one is reward model. So our reward models actually themselves have holes, right? So reward model is nothing but generally another model. So it's a model that we're training to give us something is safe or not. And we know that the reward models themselves are subject to adversarial attacks. We train these models on a lot of noisy data. They don't capture all scenarios of jailbreaks and everything else. So the reward model itself is basically imperfect, and reward modeling is hard. Now you can do some ensembling, etc., but it doesn't solve the problem. So if you're interested in this area, I think there is still a lot to be done on training better judges or better rewards. The other thing is that in practice, like another very hard question is that in practice, we need to patch models sometimes from a handful of loss patterns, right? Somebody comes up with a new jailbreak or like a new way of like prompt that basically goes wrong. And then the question is, how can you fix that, right? So of course you can come up with patches that say or do not respond to this prompt, but rather we would like to be a bit more systematic and try to actually generalize from a like small handful of loss patterns into a new reward model, or like to be able to capture the essence of those kind of loss patterns. The other issue is the prompt set. So I talked a little bit about the prompt set, right? So the prompt set has to cover a lot of the issues, like it has to cover different the jailbreaks. It has to also trigger the model to give us safe versus unsafe, so that then the RL process can actually learn from these things, right? So to be able to capture and distill it into a new model, the prompt set itself is important. Now, let's say one issue that may come up is that we have a prompt set. It kind of triggers the model, and then we can actually get unsafe responses and so on and so forth. We train the model, right? Now, in the generation 2 of the model, we have already patched the model to be safe against these prompts. So we need again new prompts to be able to trigger the model. So the methods that Ahmad talked about is very, very important, because now it's an automated way that is jailbreaking, gives us an automated way of triggering the model to be able to kind of find the prompts that trigger the model to give high or low reward and learn from that. Now, one thing I didn't talk about is like these offline methods like DPO that do not do rollouts of the model. They are generally a lot less robust, and so like robustifying that is also a problem. Now, Ahmad also talked about like multilingualities. Like once you go to other languages, generally models become a lot less safe because there is a lot less data. So the question is, how can we think about basically building these things in a way that work for everyone and in all languages? Now, one thing I want to say and conclude is that, so Ahmad showed that there is a lot of different types of attacks that can basically trigger the model. So this is what I'm showing here is attack success rate for a pre-filling attack. So Ahmad actually described this pre-filling attack. So it could be like a simple way of pre-filling attack is tell me how to make a model. Sure, here is how to do it. And then basically prompt the model with that, right? So it makes it more likely for the model to actually generate the instructions for creating a model. And here I'm showing the attack success rate for the base models, so Llama-based models and the Gemma-based models, versus basically the aligned models. So these are basically instruction-tuned RLHF models. So you see that without pre-filling, these models are very, very safe. So they get like 0% attack success rate, whereas the base models have like high attack success rate. But then when you start pre-filling just a few tokens, like 7 tokens, 10 tokens, all of a sudden this attack success rate goes above 50%, right? So, and this is just not pre-filling, this is like there is a lot of different types of attacks that can trigger these models. And one thing that we identified is that there is a common underlying phenomenon that is the culprit for this case, is that basically when we do the fine-tuning of the models, we are mostly touching the probability distribution over the first few tokens. So mostly teaching the model to refuse. So when it's saying, tell me how to make a bomb, we're going to increase the probability that the first few tokens is I can't help you with, right? But then we're not really touching the probabilities after this pre-fill. Like, so if I say, tell me how to make a bomb, sure, I can help you with that. The probability of generation after that hasn't really been touched much. And that's what I mean by the safety alignment is shallow, because we're only basically touching the distribution and the probabilities over some typical use cases of the model. And that's basically part of the reason that these are so vulnerable. Okay, with that, I'm going to conclude. So hopefully after this session, everybody's convinced that best of it is the way to go. It is a very simple method, right? That everyone can try out. And you can just inspect a few responses. You can look at the best one. You can also verify that the best one is actually the best one that you yourself prefer. So in a sense, you can also verify your reward model. It's essentially Pareto optimal for reward versus KL. So it's actually not just the heuristic or like a baseline. It's actually a great method. It's just expensive. Now, if in an application, you can afford n equal to 100 or 1,000, then you don't even need to train a new model. You can just use best of n, right? It's just 100 to 1,000 times more expensive. Much easier to debug. And then when training a model using alignment, we should be tracking the KL divergence, right? If the KL divergence is above 100, then it's probably the model is not useful. But you can look at the responses. It's definitely I mean that's where my money would be. It's basically already reward hacking. KL larger than 15 is probably reward hacking for the most part. Now there are some applications where like translation or like some more deterministic applications where like a KL of 15 may be okay, but for the most part that's in reward hacking regime. And then KL less than 8, I think you're probably in the clear. And that's the regime where you want to be operating. So this is the part that I didn't talk about, but the RLHF framework generally assumes sampling from the model, but we don't sample from these models. We're generally using now more and more sophisticated test time algorithms, and there is a way to try to fix this. And yeah. Okay, so this is some of the references of our work that I talked about, but I talked about a lot of other work as well. And with that, I'm just going to stop.